Hi everyone, welcome to this presentation on non-parametric alternatives for t-tests. Non-parametric alternatives to t-tests are actually needed in several situations where the assumptions required for t-tests are not fulfilled. In the earlier lecture, we talked about some of the assumptions for t-test. T-test relies on several key assumptions for its validity, including normality of the data distribution and homogeneity of variance. So when these assumptions are violated, the results of t-test cannot be trusted and it can often be misleading. So let's look at some of the situations where the conditions for compliance would be required for t-tests, normally normality here and the homogeneity of variance. So here are the assumptions for a normal t-test that we discussed in the previous lecture. Essentially the normality where the normality of samples is important. If this condition is violated, then we have to consider non-parametric tests. Similarly, the homogeneity of variance between two sample groups, let's say sample group 1 and sample group 2, the data presented here to the t-test, the variance here should be more or less similar. That means the samples should be drawn from the same population. If the variances are different here, then we have to consider non-parametric um, version of t-test. That is what we are going to talk about in this presentation. So, what are the non-parametric alternatives? So, one is the Mann-Whitney U-test. That is what I'm going to cover in this discussion, and Wilcoxon signed rank test. The first one is meant for independent pair of samples, and Wilcoxon is for the paired data. For example, the patient records and the before and after treatment scores. So we will go through both of them and we'll try to understand how they actually work. Um, there are other reasons why we will consider non-parametric alternative like Mann-Whitney U-test and Wilcoxon sign rank test. Other reasons could be the small sample size. So sometimes we have a small sample size, then that may not give you a true reflection of mean and variance. And non-parametric tests, which are based on ranks rather than the raw data, so it is less sensitive to the distribution of data. One more reason could be outlier and the heavy tails. The outlier and the heavy tail distribution can also influence the results of a normal t-test, potentially leading to incorrect results or conclusion. And again, non-parametric tests are more robust to outliers. The reason is we are not using the raw data directly for the test, but we use the rank. Similarly, ordinal data, normal t-test requires the data to be continuous, interval or ratio. When dealing with ordinal data, the differences between the levels are not equal, so that cannot be used with the normal t-test. Again, the non-parametric versions of t-tests are more appropriate. So these are few reasons why would we consider the Mann-Whitney U-test and Wilcoxon sign test. So let's get started. So the first one that we're talking about is the Mann-Whitney U-test, which is also called Wilcoxon's rank sum test, not Wilcoxon's signed rank test. So these are two different things. The first one is a Mann-Whitney U-test, and this is essentially comparing the difference between the two independent groups. That means you have sample 1 and sample 2. For example, this is sample 1 and sample 2 presented to this Mann-Whitney U-test. So when do we use? When we have ordinal data or interval or ratio. So essentially we use most of the time, the data is going to be float or continuous, and that's where the Mann-Whitney U-test is going to be used. useful. Essentially, we are going to compare the medians of two distributions. For example, distribution 1, distribution 2. Instead of the mean, we are going to use the median here. Okay, and the median of two independent groups, especially when the data does not meet the assumptions for t-tests like normality and the homogeneity of variance. All right, so essentially how we will perform the Mann-Whitney U test. Uh, we will use SciPy package, which is basically a one-liner, but I'm going to detail it out so that we understand what happens in the background. So the Mann-Whitney U test, we are going to combine the data first. So for example here, so let's say the group 1 and group 2 data, and we are going to concatenate both of these. So that's the combining of phase. After combining the data from both the groups, we are going to assign the rank. That means after combining, let's say this is a resultant group. So we're going to rank it 1 to 17, 77, and all that based on the values in the combined series. And if there are any ties, then the algorithm will assign to each tied value the average rank that you would actually be giving. So for example, there is a tie between these two. So we will take the average of this and put it like, for example, this is 7 and 8, and they are tied. So this will be 7.5. So that's the first thing that we do, combine the data and also the ranking. Post that, we're going to calculate the sum of the ranks for each of the group. And then we call the sum as R1 for group 1 and R2 for group 2. Use the rank sums to compute the U statistic. Now, instead of T statistic, we have U statistic here. So for each of the group, we will have U statistic. For example, this is going to be U1 for sample group 1, U2 for sample group 2. All right, so there are formulas to compute the U1 and U2, and essentially the number of samples in group 1, number of samples in group 2, and then we have the multiplication here, the number of samples divided by 2, and subtract the rank here. For other group also, we follow the same pattern. So this is going to give you some number like 17 and 27, just for example. And we are going to pick the smaller of the two. For example, U1 is smaller, and that is the statistic for us, or U statistic for us. Now, why do we consider smaller of the two? The reason is we take the minimum of the two U values, U1 and U2, to ensure we're looking at the extreme. And that's the fundamental objective in inferential statistics. We look for data which is very extreme. And that extreme leads us to make the conclusion whether that is extreme is by chance or by random. Now, so for any given data set, one of the values, let's say U1 and U2 would be small if there are differences, right? Indicating a significant difference. So one value will be small, the other one will be high if there are any differences in the data. And we are interested in the tails of the distribution. Essentially, what does it mean? It means, let's say, in our previous t distribution, just one second. Yeah, so in our previous t distribution, for example, this is how the distribution is. We are more interested in the extreme area. So this is like extreme area. And if your sample falls, or the U statistic falls in this region, either this region or this region, and then we are in a position to make a decision whether that should be accepted or rejected. So by taking the minimum of U1 and U2, you are actually focusing on the smaller value, which is easier, or which is really useful for us to make a decision. And that's why we consider smaller of the two values. So let's see an example here. Let's say the group 1 data consists of these values. and group 2 data consists of these values. So we're going to combine them. So we combine them, and that's the resultant combined data. And then you assign a rank. So this is already sorted. So it's like the rank is also going to be 1, 2, 3, 4, like that. Okay, and then what we do, use this rank to rank the data in group 1 and group 2 individually. So these are the ranks here, 3, 4, 5, 1, 2. So now you notice we are not using the raw data for computing this statistic. We are using rank instead. So there is another abstraction on top of the raw data, and that abstraction is called the rank data. And we use the rank data to compute the statistic or U statistic. So sum them up, and that is the sum of the rank for group 1, sum of the rank for group 2, and we will pick the smaller of the two, which is going to be 15 in this case. Now we compute the U for each of the groups. So this is what we substituted, and we get the value U1. For example, this is just for example, 25 and 0. So if you had U1 as 25, U2 is 0, then the minimum of the two is 0. So we pick the U statistic as 0. So U statistic can never be negative. This is one fundamental property here because it's about rank, right? So rank means it cannot be negative. The U statistic is a measure of rank difference between the two groups, and it is always a non-negative number. The range of value which the U statistic can occupy is 0 from 0 to a maximum of number of samples in group 1 multiplied by number of samples in group 2. For example, 5 and 5. So the maximum value will be 25. Now, in the non-parametric test, which is Mann-Whitney U test, the distribution is going to be approximated by a normal distribution. Now, this is fundamental to understand why we consider normal distribution as an approximation for this inferential technique. So U statistic, as you have learned, it is from the ranks of the data combined together. And for small size, let's say you have very few examples in group 1 and group 2, for less than 20, less than 10, for example, then the distribution of U statistic can be exactly determined by using some tables. So these tables are statistical tables, and they are available online and also available in many of the literatures and textbooks. So by consulting or referring to the tables, you can compute the U statistic, or you refer to the U statistic from those tables, and this is for small sample size. Now, compared to the small sample size, if you have large samples, then computing the exact distribution becomes impractical. And now we're going to use an approximation method. So when we talk about approximation method, that means we need to approximate the data, which is ranked data, in terms of a mean and standard deviation. So this is the mean and standard deviation of ranked data, and this is the formula for that. So once you have determined the mean and standard deviation, you can come up with a distribution or a probability density function and cumulative density function. This is why we use the normal distribution as an approximation for the distribution to be used in Mann-Whitney U-test. So the implications for hypothesis testing in this case will be how the critical values and the p-values will change because of the mean and standard deviation. And if they change, then the shape and the distribution changes, and hence the critical values will also change. So we need to determine the critical values from this distribution using the alpha or a significance level that you have set. And then we compare the critical values with the U statistic for the final conclusion. So that's pretty much the outline of this non-parametric test called Mann-Whitney U test. And I'm going to show you a Python code in a while. Okay, so here is the Python example. I will illustrate step by step how each of the step is performed in Mann-Whitney U test. So the package is going to be the SciPy here also, and I'm going to generate some random data and make sure the data is non-normal. So I'm using exponential distribution for specific reason. And the plot of the data will show you the data is really exponentially distributed, not a normal distribution. And if it is not normal distribution, then your normal t-test will not be applicable, or you should not use the normal t-test. So the step is to concatenate the group 1 and group 2. So we concatenate here. Then we rank the data based on the values using a stats package. And the stats package takes the series and rank the values. Now we also create the rank 1 and rank 2 for the group 1 and group 2. So those are the ranks for the data in individual sample groups like group 1 and group 2. Then we compute the U statistic for each of the group using the formula that we discussed in the slides earlier. So that's my U1 and U2, and we consider the smaller of the two as the statistic or U statistic. In this case, is going to be 335. Now we can validate if 335 is right by using the Mann-Whitney U package directly, and we use the group 1, group 2, and the alternative is two-sided because this is going to be a two-tail test. So that's going to return me a U statistic, which is same as what we got by manual computation. And the p-value also can be used for conclusion. So if this p-value is higher than 0.05, so you will not be able to reject it, the hypothesis here. All right, so the alpha is, let's say, 0.05. And since this is a normal distribution, so firstly, the distribution mean and the distribution standard deviation, as per the formula, we need to create it or compute it, and that's the mean and standard deviation. And then we compute the z score values for the critical value that we have alpha here, and that's my alpha or u value here, critical value, and then we plot it, and you notice here, okay, I need to define the x here, just one second. Yeah, so this is the plot. So my rejection region is on this side. So the red line is my critical value. If your test statistic falls on the right hand side of this, then we have a case of rejection. But our line or test statistic falls on the left of it, that means we cannot reject it. And that is what we saw, the p-value was 0.09. And that is not less than 0.05, so we cannot reject it. So it's pretty much validated, and this is how the Mann-Whitney U test is, done manually and also using the package. Okay, so that was the demo using a Python code showing the Mann-Whitney U-test. Let's continue and we'll talk about one more non-parametric test, alternative for normal t-test. But this time, this will be not for individual independent samples, but it will be for samples which are dependent. So what does it mean? It means we have two sample groups, but the value here and value here are paired. So, for example, a patient, measurements before the test and after the test. Another patient before the test and the same patient after the test. So that's the paired data. So in such case, we cannot use the Mann-Whitney, but we have to use the another non-parametric test called Wilcoxon signed rank test. There are similarities, but there are some differences as well. So let's see what are those differences and where the similarities are. So when to use Wilcoxon? When we are talking about repeated measurements or paired measurement or matched samples. That's where we use the Wilcoxon signed rank test. The differences between the pairs are continuous or ordinal. Now, this is an advantage here of the non-parametric test. You can also use the ordinal data and as well as the continuous data. With the usual t-test, you cannot use ordinal data. All right, so this is when we apply this. And also the conditions of normality is missing in the data. And that's when we use Wilcoxon signed rank test. So assumptions are the paired observation, it should be paired observation, and differences are symmetric. So we are going to compute first the differences between the pair. Then now we're going to rank the differences, which was not the case in the Mann-Whitney U test. We looked at the absolute values of the data and we ranked it, but here we will make the difference between the readings or difference between the samples, sample 1, sample 2, and then we rank the difference itself. Okay. And then we assign a sign also here. Sign means positive difference or a negative difference. So for a particular difference, let's say it's minus 10, then it will be the rank of 10 and also include minus sign. So for positive also, it will be the same thing. Let's say the difference is 5 plus 5. So it will be positive and the rank of 5. So, and the next step is sum the rank. This is similar to what we did in a Mann-Whitney. So sum of the ranks for positive differences, sum of the ranks of the negative differences, plus and minus. Test statistic is going to be smaller of the two. Again, the reason we are looking at this smaller is we are looking for extreme. And the null hypothesis is saying that the no difference in the median. And then we use the usual, process of determining the critical value for a given significance level and a p-value to make the conclusion. So the difference between the Mann-Whitney U test and Wilcoxon signed rank test. So this is used for independent pair of groups, independent sample set, not pair. Okay, so here we are using the paired sample, so where we have two samples and the values are kind of related to a common entity, a patient or a student or machine. Okay, and the purpose is here to compare the distribution, and here they compare the distribution of differences. Test statistic is the rank of all the observation combined. Here signed rank of the differences. I hope this is now clear. Let's go over to the Python code and see how Wilcoxon sign rank test is performed. Okay, so let's take a look at the Python code for Wilcoxon signed rank test. Again, here SciPy is the package. And I'm going to generate some data here. And this is how the data looks like. And I'm not going to use t-test on this data. So, and since this is the paired data, so I'm going to use the difference of the samples. So group 2 minus group 1. And so remove the zeros. This is the additional thing that we have to do. If there are no differences, just remove it because we're not interested in zero difference. So just remove the cases where the difference is 0. Then we rank the data. So the rank the data means is going to rank the data by looking at the absolute value only. Okay, and based on the absolute differences, is going to rank it. And after that, we're going to apply this signs, mean if there was a positive difference or a negative difference, restore it. So we just multiply here the rank with the sign of the differences here. So this was like minus, so now minus appeared. This was positive, so this positive also came in. After that, we do a sum of the positive and negative. So these are the sum here, 301 and 164. So the statistic is going to be 164, and you can verify here by using the SciPy also that we get the same value. as 164 as the test statistic. The p-value returned is 0.0164. That means it is more than 0.05, which is our alpha. So we will not be able to reject the null hypothesis. I hope this code is pretty straightforward and it demonstrated the idea of differences and then create the rank. Okay, so that's pretty much it in terms of non-parametric alternative for t-test. In the next video, we'll talk about another inferential technique uh, called ANOVA. So thank you for watching, and we'll see you in the next video.